Welcome back to another Timberwolf Tutoring video. In this video, we will be covering concavity. We will first be going over concavity conceptually. Then, we will move on to 3 different examples.
So now that we're done with extrema, we have the equally fun topic of concavity, which is a bit difficult to understand conceptually, but take some practice, and once you get it, you get it. So, if you look at this graph here, which the function is over here is y equals 1 over x minus 1, you can see that on this side of the graph, which way is the curve facing? And you can sort of imagine that this curve encompasses this area up here. You can imagine that it sort of looks nicer than this area because the curve is facing inwards. And so you can imagine that this curve is concave upwards because the area encompassed by it goes upwards. And similarly, this one, the curve is it looks like it's facing downwards. So the area under the curve is facing downwards. And so that's basically what concavity means, is which way is the curve facing. And for a graph like this one, usually it's pretty obvious which way it's facing. But there are more complicated graphs, like this one of this function here. And you can see that on this left side, the graph is definitely curving to be facing that way. And same on the right side. And in the middle here, it's definitely facing downwards. But it's not immediately obvious at what point it changes from upwards to downwards and back. So to do that, we look at the tangent line. And again, here's your tangent line here. And this is the tangent line at -4. And you can see that as the tangent line moves along the function, slope's increasing, increasing. And the slope increasing means that the function is concave upwards, because it's curving upwards as it goes on. And you see the slope still increasing, but watch what happens when it gets to x equals -1. So you see the slope will just suddenly stop increasing right here. And at -1, it'll actually start decreasing. So what this means is -1, x equals -1, is what's called a point of inflection, where it changes concavity. And same here at x equals 1, you can see it stops going from decreasing and starts increasing again. So x equals 1 is also a point of inflection. And what this means is it's concave upwards from -infinity all the way over to x equals -1. And it's concave downwards all the way from there until x equals 1, and then concave upwards to the rest until infinity. So how do we solve this algebraically? What we want to do is, the slope of our tangent line is obviously the derivative. And so here's the graph of the derivative function. Or sorry, not that one, it's this one. And you can see that the derivative is also increasing. This is the slope of the tangent line over time. And you can see that right here at -1, the slope of the derivative stops increasing and starts decreasing again. And then right here it starts increasing again. So you can imagine that we'd want to figure out the point where the slope of the derivative function it changes from increasing to decreasing. But how do we find the slope of this function? By taking the derivative again. So we want the second derivative here. And it turns out when you take the second derivative of this function, that's actually how you find concavity. So what you can do is, if the second derivative is greater than 0, that means that your derivative is increasing and you're concave upwards. If it's less than 0, you're concave downwards. And if it's equal to 0, like right at this point, at your extreme on the derivative function, then and only then we have a point of inflection. So now that we know concavity, we'll take a look at one more example. This function, y equals x to the 5/3. Weird power, I know. But you can obviously see where the concavity is. Let's solve it algebraically. And we can see that this is the derivative function, and it's a second derivative function. Bunch of graphs on here. So the green function is our original function. When you take the derivative of it, it looks like this. And you can see here that the second derivative at x equals 0 actually doesn't exist, which is weird. So what does this mean? It's not equal to 0, but it's still a point of inflection. So the other case is when the second derivative of this function is equal to not existent, or does not exist, then it will also be a point of inflection. And notice that even though this original function is differentiable, even differentiable functions can have non-existent second derivatives, because it turns out the derivative of this is also not differentiable, even though the original function is. And so I hope that helps you understand concavity a bit better. It's a weird topic, takes practice, but let's get some practice in right now and look at a problem.
Alright, so for our first example, we have determine the intervals where the graph of f of x is concave up or concave down. And our function is f of x is equal to x to the 4/3 plus 4x to the 1/3. And we can use a second derivative to determine concavity. In order to find the second derivative, we must first find the first derivative. So if you'd like to pause the video here and find the second derivative, go ahead. So in order to find the first derivative, we can use the power rule. So we bring down the 4/3, multiply it by x, subtract 1 on top, and then do the same over here. Bring down the 1/3, multiply it by 4x, and subtract 1 on the top. So this is our first derivative. And we find the derivative of the derivative to get the second derivative. So the second derivative is right here. And we can simplify this even further and put it into factored form. And the reason we do this and put it into factored form is because it makes it easier for us to find the inflection points. And the inflection points are where the function is either equal to 0 or at points where the function does not exist or is undefined. So let's find out where the function is equal to 0. If we plug in 2 over here, then 0 times any of these terms is still 0. So that's one of our inflection points. So the derivative is equal to 0 at x is equal to 2. And that's the only point that we can plug in to result in the function being equal to 0. So we can move on and find out where the function does not exist. And we know that 0 to any negative power is undefined. So that is where the function does not exist, and x is equal to 0. And now that we have both our inflection points, we can determine the concavity between them, using a point between these two inflection points. So between 0 and 2, we have 1. So we can plug in 1 back into this function, the second derivative. And then once we plug in 1, the output is less than 0. So we know that f is concave downwards. If the point was greater than 0, then the function would be concave upward. So now that we know the concavity between this interval, and this is an open interval because 0 and 2 are not included, we can find out the concavity on both sides. So on this side, we have negative infinity to 0. So if we plug in a point between this, the resulting value would be greater than 0. And we know that f is concave upwards on this interval. And on the right side of this interval, we have 2 to infinity. And if we plug in any value in between these two, we get a positive value output. So we know that the graph is concave upward. So now we've determined the concavity between this interval and on both sides of this interval. So that's the entire graph. And we've solved this problem. And now we have another example problem.
Right, so next up for problem 2, we have a similar problem. It says determine the intervals where the graph of f of x is concave up or concave downwards, and our function is x squared plus 1, or x squared minus 1 rather, all over x. So how do we do this? Well, concavity is determined by the second derivative. So first up, the easiest thing to do is rewrite this function a little bit, and we can divide both x squared by x and negative 1 by x to write this as x minus x to the power of negative 1. And that'll make it a lot easier to take derivative, because now we can just use straight power rule instead of quotient rule. So first derivative of this is just 1 plus x to the negative 2. Second derivative is, and pause the video at any time if you want to solve this yourself. But this would be equal to 2 times x to the negative 3, except it's negative now, because using the power rule, the 1 disappears, and since the coefficient on x to the negative 2 is 1, multiply 1 by negative 2, get negative 2. Alright, so now that we know the second derivative, we want to find the points of inflection, which are when this is either equal to 0 or doesn't exist. So to do that, first we check if anything is equal to 0, and it turns out there are no values of x that work here. And then we check if it doesn't exist at any point, and that would be at x equals 0, so you can't take 0 to a negative power. So the only inflection point is at x equals 0. So now all we have to do is test a point on either side, because there are only two intervals. negative infinity is 0, and 0 to positive infinity. So we test a point in each of these intervals and plug the derivative into it. So first we check 1, and we plug it into the second derivative function, and it's less than 0. That means that the function will be concave downwards on the interval 0 to infinity. And then you can go ahead and check negative 1 or negative 100 or whatever number you want to determine what the concavity is on the other side. I would recommend pausing the video and working that out for yourself. But anyway, now that you've done that, we can say that f is going to be concave upwards on the interval negative infinity to 0. So now we have all the concavity for this, we're done. And the point of inflection is at x equals 0. So now, here's a bit more complicated problem. We have to find all critical numbers on this function and classify either one as a relative minimum, relative maximum, or neither. So to do this, we can use second derivative test once we found the critical numbers. And it turns out, from the last problem, since it's the exact same function, we already know what the first and second derivatives are equal to. Which is great. That shortened a lot of work for us. But anyway, so the first thing to do is find all critical numbers. And we know from extrema that critical numbers are where the derivative of the function is either equal to 0 or doesn't exist. So first, where is it equal to 0? And if you look closely at it, if it's equal to 0, x to the negative 2 would have to be equal to 0. And what values satisfy that? Think about it for a second. And the answer is there are no values that satisfy that because the power is even, so this will always be positive unless the number is imaginary. So now, when does the derivative not exist? Well, think about that for a second. And it turns out it will not exist at x equals 0. So this is our only critical point. So now, how do we tell if it's minimum, maximum, or neither? We use the second derivative test on it. So what that says is if the second derivative is positive, it's relative minimum. If it's negative, it's a relative maximum. And if it's not, it doesn't exist or is 0, then it's neither. So plug 0 into your second derivative, see what you get. I'll give you 10 seconds. Right, so you've got your 10 seconds. Now, it turns out that the derivative of this also doesn't exist because you can't take 0 to a negative power. So what this means is x equals 0 is neither a minimum or a maximum on this interval. And we solved it. So great. At this point, hopefully you understand how concavity works a bit better and the second derivative test here. And now that you understand this a bit better, I'm glad we could help, and thank you for watching.
Thank you so much for watching our video. If you want to contact us, you can reach out to us on email at timberwolftutoring@gmail.com or on Instagram at timberwolftutoring. Let us know if you have any questions about the topic covered in this video, or if you want to see a specific topic covered in the future. Be sure to subscribe and turn on notifications so you're not missing any of our latest videos. This is Aiden and the rest of the Timberwolf Tutoring team signing off until next time. Thank you again.
Your nights, they keep on flashing. Night life is speeding, soon you'll be crashing.